Lecture 12, Calculus 3. So let's continue. We were doing line integrals. So we saw the concept of line integrals. So you have the following setup. You have a D domain in R3 and you have a curve C. C is inside D. Let's say be inside D be a curve inside a domain D in R3, and you have a function f which is from D to R3. So this is a vector field, and we saw the concept of integral f bar dot dr bar on C, and this is called the line integral of f bar over curve C. So this has a meaning in physics. It measures the work done by the force in moving the particle from one end of the curve to the other in this oriented direction. So the first thing to do, well, let's see. Let f bar be mi bar plus nz bar plus pk bar, and r bar be xt, r bar t be xt comma yt, xti bar plus yt z bar plus ztk bar. Then we proved that this quantity is exactly integral, and let's take t between say a to b. This is integral from a to b m xt yt zt. M and p are functions of three variables. That goes without saying, so I don't want to write down the variables, otherwise it becomes too long. So I will just write it as m x prime t plus n y prime t plus p c prime t dt. So let me make few remarks on this concept, and then we will continue with doing few more problems. So remark number 1, integral f bar dot dr bar over C is also written as integral f bar dot t bar ds over the curve C. Now I think I denoted by the unit tangent vector capital T bar, but here I will use small t bar. So where little t bar, which depends on little t, this is the unit tangent vector at r bar t, or I want to write this also as in terms of the arc length parameter s. So t bar t or t bar s, you can think of this as a function of s. You are parameterizing the curve by arc length, and the reason for this is simple. So the reason is, you see, integral f bar dot dr bar we showed is exactly integral f bar dot r bar prime t dt. Good. This means, let me write it a little more precise, a little more explicitly, by indicating f bar is a function evaluated at r bar t. So we are taking the value of f bar at r bar t and dotting it with r bar prime t, with which you can think of, and this is integral from a to b. This you can think of as f bar at r bar s, and r bar t I will write as r prime t. You can divide it by the length and times the length times dt. And now just observe that this is your little t bar. F bar dot r bar s dot little t bar. This is the unit tangent vector, and this is nothing but ds, because remember ds dt is norm of r bar prime. This we proved long time ago. It comes from the formula that s is the integral of r bar prime. So this is why you can write the same integral is denoted is exactly this if you use the arc length parameterization. So if your parameter is now arc length and the point r bar a will be now r bar at 0, meaning s is 0, and this is r bar, say let's call it L. L is the length of the curve, so this will go from 0 to L. Good. So this is another notation. So that's just one remark. The second remark is also obvious. Integral of, if you have two vector fields f1 bar and f2 bar dot dr bar, and you take the sum and you integrate it on a curve, this is exactly the sum of these vector value. This sum of the line integrals of these vector valued functions. Property number 3, and that is, I will denote, say by minus c we denote the same curve but traversed in the opposite direction. Denote the same curve traversed in the opposite direction. Then you will see that integral of f bar dot dr bar over minus c just minus integral f bar dot dr bar. You just make a change of variable in your formula, t equals minus t in this formula, and then you get what we have. So the line integral is orientation dependent. So line integral depends on the orientation of C. Having said that, so that was a quick review. And now let's do some more problems. So let's do some problems on finding line integrals. Let's take function f bar of xy to be y square I bar plus x square z bar, and C be the curve, C be the semicircle going from 0, minus 1 to 0, 1. Let's do this. So the first thing is to parameterize the curve. So first step is to parameterize C, and this you should be able to do. This is your pre-calc. So here I will write r bar t as, you can take this to be cos t comma sin t. Circle is always described by that. This is 1, 0. And now you have to make sure that you get the right curve. The orientation is the same as one which is shown in the figure. For that you will have to make your choice of A and B properly. So for t equal to say 0, if you want to get this point, that means you want cos t to be 0. Yeah, so if you do that, or maybe you can make, you want cos t to be 0. So if I make t equal to minus pi by 2 as my lower limit, then at minus pi by 2 I will be at minus 1. Yeah, that's right. So t varies between minus pi by 2 to pi by 2. At pi by 2 you will be over here, which is going to be 0, 1. So therefore, line integral of f bar dot dr bar over C is going to be integral f bar at r bar t dot r bar dash t dt. T goes from 0 to minus pi by 2 to pi by 2. And so it will be integral minus pi by 2 to pi by 2. What is f bar at r bar t? R bar t is this. F bar is, where is our f bar? F bar is y square comma x square. I didn't put x square there. So it is y square, which is, so maybe I'll write it like this. Y square comma x square dotted with r bar dash. R bar dash is minus sine t comma cos t. Well, 0 we don't care about because now there are only two components. Third component is 0. And now you use the fact that your xt is cos t, yt is sine t. So this is going to be sine square t comma cos square t dotted with minus sine t comma cos t. So this will be minus pi by 2 to pi by 2 minus sine cube t plus cos cube t dt. This is not really too hard to integrate. You have to know how to integrate odd powers of trigonometric functions. The way to do this properly is, well, we'll have to work it out actually. So let's work it out. So let me calculate integral sine cube t. So here you put u equal to cos t. So du is minus sine t dt. So that gives you this equal to sine cube t dt will be du over sine t minus sine t, which is minus sine and then sine square t dt du, which you will write as 1 minus cos square t, and that will be 1 minus u square du. Right, so when you integrate a odd power of a trigonometric function, if you are integrating sine cube, you put u equal to cos t, and then we have, let me just double check, is everything okay? I think it's okay. And then you get integral u square minus 1 du, which is u cube by 3 minus u, which is sine cube, sorry, u was cos t, right? So it's going to be cos cube t minus by 3 minus cos t. And let's evaluate integral cos cube t. That's not hard again. You put u equal to sine t here. So du will be cos t dt. So this is going to be cos cube t dt will be du over cos t, which is integral cos square t du, which is 1 minus sine square t du. And now you use the fact that sine t is u, so this is 1 minus u square du. So is u minus u cube by 3, and so it's going to be sine t minus sine cube t by 3. So going back to our integral, it's minus sine cube t plus, so our integral is minus pi by 2 to pi by 2 minus sine cube t, which we have here is sine cube, so minus sine cube t is cos t minus, so whatever we have here, right, it's minus, let me just see, Our integral turned out to be minus sine cube t plus cos cube t. I changed the color. So this is going to be, well, what is minus sine? This is going to be cos t minus cos cube t by 3 plus integral cos cube is sine t minus sine cube t by 3. And this is going between minus pi by 2 to pi by 2. So that's going to be cos of pi by 2 is 0. Cos cube pi by 2 is 0. Sine of pi by t is 1. Sine cube pi by t is 1. Minus the value at minus pi by 2. Cos of minus pi by 2 is also 0. And sine of minus pi by 2 is minus 1. And sine of minus pi by 2 is minus 1. Its cube is minus 1. So this becomes plus 1 by 3. So this becomes 2 by 3 minus 2 by 3. So the answer is 4 by 3. Good. Problem 2. So let's compute. Find the line integral f bar dot dr bar over c, where our f bar is given by yz I bar plus x square z bar plus xz k bar, and r bar t is given by ti bar plus t square z bar plus t cube k bar, and my t varies between 0 to 1. Therefore, we will need r bar dash. So let's calculate that, and let's write this chord in terms of a triple. So 1, 2t and 3t square. And so the line integral of f bar dot dr bar is going to be integral 0 to 1 f, which is yz comma x square comma xz, dotted with r bar prime dt. And all you have to do now is where you should note that your x component, your xt is, this is your curve. So xt is t, yt is t square, and zt is t cube. So therefore line integral f bar dot dr bar is 0 to 1, integral 0 to 1 yz will be t to the 5, x square is t square, and xz is t to the 4, dotted with 1 comma 2t comma 3t square dt. So it's going to be integral 0 to 1 t to the 5 plus 2t cube plus 3t to the 6 dt. So it's going to be t to the 6 by 6 plus 2t to the 4 by 4 plus 3t to the 7 by 7 from 0 to 1, which is 1 over 6 plus 1 half plus 3 by 7. And that means the common denominator is 42, 6 7s are 42, 7 6 are 42, so you will get 18 in between, and then 21. 28 plus 18 is how much? 46, isn't it? It's 23 by 21. Let me check whether my answers, which I just worked out here, are the same as what we had in my computation. Yeah, that's very good. So that's how you calculate line integral. So now we come to the next important thing, and that is the concept of a conservative vector field. Conservative vector fields. So now when you are talking about line integrals, one natural question is, can you say that the line integral between 2 points, say this is your curve r bar at A and r bar B, when is it independent of the curve? No matter what you take between r bar A, what curve you take between joining r bar A and r bar B, if the line integral is independent of the curve, then the vector field is said to be conservative, but I'll not define it that way. Let me first state a very important result of Calc 3. So a theorem. Should I call it fundamental theorem of line integrals? Probably I will formulate another theorem and then I will call it fundamental theorem of. In some books, this theorem may be called the fundamental theorem of line integrals. But anyway, let me state it. So let us take a domain D, and I will state it for two-dimensional vector fields. Actually, it is valid for even three-dimensional. It doesn't matter. So I think I can change it to 3 dimensions. And dB, I will state it very precisely. So even though some terms you may not understand, so let me say dB an open connected set. Open connected, I will comment on this later sometime. That means nice blob without holes. No, here you can have holes, but it cannot be like a fractal. So let's take a nice set and let's take a function from D to R3 be a continuous vector field. So I'm just assuming continuity of F. Then the following statements are equivalent. That means if one holds, the other two holds. So the first statement is line integral f bar dot dr bar over C depends only on the endpoints of the curve C and not on what curve it is. So as long as the endpoints are the same, all curves will give you the same value for the line integral. So this depends only on the endpoints of the curves and not on C itself. So that's your first statement. What is that equivalent to? This is equivalent to saying that f bar dot dr bar over a closed curve is always 0. For any closed curve, let me add the word, well, when I talk about a curve, I am always assuming that the curve is smooth and regular. So any simple, smooth, regular, I'm always assuming smooth, regular. So what is a simple closed curve? That means it avoids figure 8 situation. You have a nice loop like this. This is a simple closed curve in the domain D. So for any simple closed curve, closed means its initial point and the final point must be the same. So that's what is meant by closed curve. So r bar t for t between A and B is closed if r bar at A equals r bar at B. Okay, so Saying that the line integral is independent of the curve and depends on the endpoint is equivalent to saying that it's the line integral on any closed curve is 0, and the third and the most important condition is the following. This is equivalent to saying that f is a gradient of a C1 scalar field. So there exists a C1. C1 means of class C1. That means its partials of first order are continuous. So C1 scalar field phi from D to R such that f bar is gradient of phi. So f at any point x, y, z is gradient of phi at any point x, y, z for all points x, y, z inside D. So in other words, those vector fields which come as gradient of a scalar field have the property that the line integral is independent of the curve joining them. So now, as a corollary, I can also mention one more thing. So corollary, if any one of those is true, if any one of the condition holds, then you can actually see that line integral of f bar dot dr bar over any curve C is just going to be the value of this phi at the endpoint, which I will call r bar b minus phi at r bar a, where C is any curve joining r bar a to r bar b, and phi is the one which is given in part 3. So phi is such that the gradient of phi is f. Physics people like to call this phi a potential. Let me give you a quick proof of this. The proof of this is easy, because suppose f bar, if you are computing an integral on C, and let us take a curve C to be some r bar t, which is xt comma yt comma zt, and I'm taking t between a to b, then what will this integral be? This integral is going to be f, because f is satisfying above condition, it is gradient of phi dotted with r bar prime t dt from a to b. But this is exactly same as integral d phi dx comma d phi dy comma d phi dz dot product with dx dt comma dy dt comma dz dt dt from a to b. But you see, if you take the dot product, what you get is you get d phi dx dx dt plus d phi dy dy dt plus d phi dz dz dt. And now you should remember your chain rule. This is exactly, if you think of phi is a function of 3 variables, but then each of them depends on t. So you are taking phi as a function of one variable by composing it with the function t goes to xt comma yt comma zt. So this is just the total derivative of phi with respect to t by the chain rule. So this will immediately say that you are integrating a function which is a derivative of another function. So this is phi at x at b comma y at b comma z at b minus phi at x at a, y at a, z at a. So that's the proof, which is phi of r bar b minus r bar a, phi at r bar a. So in other words, if vector field is a gradient of a scalar field, then the line integrals are independent of the path. So now we make this definition. A vector field is called conservative if any one of these conditions holds. So definition, let F bar from D to D, which is a subset of R3, to R3 be a continuous vector field. Then F bar is said to be conservative. This terminology you might have heard in physics. If any one of the above three equivalent conditions hold. So in particular, maybe in physics class you take the following as the definition. In particular, this means F bar is gradient of phi for some C1 function, C1 scalar field phi. And as I said before, maybe I will add, phi is also, or is called, in physics terminology, it is called the potential generating the force field F. Potential generating F. Good. So now this doesn't tell us how to actually check whether a vector field is conservative. So the question is, how do we check? How do we check whether a given vector field is conservative? Now we'll find a necessary and sufficiency condition which is easy to check. So first observe, so suppose, I will write this as a lemma. Suppose now I make one more assumption that my F is not just continuous but is of class C1. Suppose F bar from D, which is a subset of R3 to R3, be a C1 vector field. And let me state it now first for vector fields in R2. So let's take a vector field, say F bar is M I bar plus N Z bar. M and N are functions, right? M and N are functions from D to R. And if F bar is conservative, then partial of M with respect to Y at any point xy must be partial of N with respect to X for all xy's in D. Let me give you a quick proof of this. So since F bar is conservative, what do we know? Since F bar is conservative, F bar is the gradient of some scalar field for some phi from D to R. Phi is of class C1, meaning its first partials are, they exist and are continuous. So what does that mean? That means Mi bar plus Nz bar, which is F bar, is also gradient of phi, which is d phi dx I bar plus d phi dy z bar. So that means M is d phi dx on D and N is d phi dy. These are functions, so when I say on D, I mean they are equal to each other at every point of D. Now we use the fact that because f is of class C1 and the partials of phi are going to be the components of f. So since f is of class C1, phi is of class C2. Because look, phi, its partials are m and n. And you know that f is of class C1, that means partials of m and n both exist. So that means the second partial of phi both exists and are continuous. So now we use a theorem which I have mentioned before, but I haven't written down the statement precisely. If a function is of class C2, then its mixed partial derivatives are the same. So I want to state this theorem, but how should I write it here? So phi is of class C2, therefore phi of xy is phi of yx. This is what the theorem says, which I will write at the end of this proof. But what is phi of xy? Phi of xy means you differentiate with respect to y phi x, but this is dm dy. And what is phi of yx? You differentiate phi y with respect to x, but this is dn dx. Therefore, dm dy equals dn dx. So this is an important sufficiency condition for vector fields of class C1, a necessary condition for vector fields of class C1 to be conservative. Right? The converse is also true, provided your domain D is so-called simply connected, which means it has no holes. So let me write this remark first. The converse it's true is also true. I will write this as a separate theorem in a minute. So the converse is also true if D in quotes I say has no holes. In technical terms, D is simply connected. So what is simply connected? We will not worry about that at this point, but I will mention. So first of all, also another thing, before I write this as a theorem, the theorem that I used here, we used above, in the above proof, we have used the following result. Lemma: if phi is a function of two variables, d in R2, taking values in R, is of class C2, then phi xy at any point xy is phi yx at any point xy for all xy in D. So if you have a twice continuously differentiable function, means its first and second ordered partials exist and they are continuous, then the order in which you take the partials does not matter. So that is what we have used here to prove that result. And so now comes the theorem which I mentioned as in the first part of the remark. So let us take a vector field f on D, which is a subset in R2 with values in R, be of class C1. That's my first assumption. And let D be simply connected. I will tell you about this sometime later. This means it cannot be like Swiss cheese. It cannot have a hole in the middle. Pancake without a hole. So then you have the following. Say f is given by mi bar plus nz bar. Then f bar is conservative if and only if we proved one implication. If f bar is conservative, we showed that dm dy is dn dx, and the converse also is true on D. So not at just one point, but at all points. So this theorem, along with the previous theorem that I mentioned, is called the fundamental theorem of line integrals. So this theorem, can I call this theorem 2 and the previous one theorem 1? That will be better. Previous theorem was that those three conditions are equivalent. So I call this theorem 1, which tells you that these three conditions are equivalent. And then if your region is nice, meaning it's simply connected, it's also equivalent to the fourth condition, dm dy equal to dn dx in 2 dimension. So these theorems I will call these theorems. Let's do the erasing more. These theorem 1 and 2 collectively is called the fundamental theorem of line integrals. And this is perhaps, I think, the most important theorem that you study in Calc 3. I shouldn't say that because we'll study another important, maybe is the first important theorem in Calc 3, because we are going to study Green's theorem, Stokes theorem and divergence theorem in time to come. Those are also very important. So this is a very important theorem in mathematics, of course. And this is the first important theorem that you learn about in Calc 3. And I think the previous things were not as important. First important theorem in Calc 3. So now I want to tell you, using this criterion, how to check whether a given vector field is conservative or not. And then we can, if it is conservative, we can also find the line integrals very easily. And how do we find this phi? That we will check. So let's see some examples. So let's talk about problem 1. Let f bar of xy be 2x plus 4y I bar plus 2x minus 2y z bar. Is f bar conservative? So now we have a criterion to check conservative vector fields. The only thing is you have to check that your function is of class C1 and the domain has no holes. So I should say functions components are polynomials. So this function is infinitely differentiable. So it's clear. So note that you should always write things precisely. Note that f is of class C1 because m and n are polynomials. So you can differentiate them as many times as you want. So certainly 1 times. And the domain of f is, again, these are polynomials. So domain is all of R2. And domain of f bar is R2, which has no holes. Yeah. So therefore, whether it is conservative or not is going to be dependent by checking dm dy equal to dn dx. Therefore, f bar is conservative if and only if dm dy equals dn dx. So shall we, so this is your m, this is your n, so dm dy will be d dy of 2x plus 4y, which is 4. dn dx is d dx of 2x minus 2y, which is 2. So they are not equal, so dm dy is not equal to, they are not equal at any point, in fact. So you want them to be equal at all points. So dm dy is not dn dx at any point of d. So even if you don't have that for one point, the theorem is not true. So therefore f bar is not conservative. Let's see another example. Let's take this function to be 6xy plus 2y square minus 5 I bar plus 3x square plus 4xy minus 6 j bar. So this is your m, this is your n, and again as before, these are polynomials. Since m and n are, when you apply a certain theorem, you have to verify that the hypothesis holds. So notice that the domain of f bar is all of R2, which has no holes, and your functions m and n are of class C1. Since m and n are polynomials, m and n and hence f as well are of class C1. Domain of f is R2. So f bar is conservative depends on checking whether dm dy equals dn dx. So f bar is conservative if and only if dm dy equals dn dx. So let's check dm dy. This is going to be 6x plus 4y, and dn dx is going to be 6x plus 4y. Voila. So therefore dm dx is equal to dm dy equal to dn dx for all points, at all points in D, and D is R2. Therefore f bar is exact. Now we will not exact, it's conservative. The differential equation is said to be exact. So now we learn how to find the potential phi. So now we know by our first part of the theorem that because it's conservative, there is a phi for which f bar is the gradient of phi. So now we know that there is a phi from R2 to R such that f bar is gradient of phi. So let's find phi. So method of finding phi. So let me illustrate that in this problem. So what do we know? We know that d phi dx must be m, which is 6xy plus 2y square minus 5 and d phi dy is n, which is 3x square plus 4xy minus 6. So now with given these two things, finding phi, this is your first experience of solving a partial differential equation. Finding a function of two variables whose both partials are given to you. So how do you do that? So naturally, let's start with the first one. What does that say? So phi of xy, I integrate both sides. So this is going to be integral of mxy dx, yes, plus something, but when integration is not unique. So you can add anything which depends on y, and when you take the partial with respect to x, this constant, which will be a function of y now, so I call it psi y, that will vanish when you take the partial. So the first condition, d phi dx equal to m, says that phi must be integral of mxy dx plus some function for some function psi of y. So then you can see what this will be. M is going to be, what was the m? M is 6xy plus 2y square minus 5 dx plus psi y. And so this is going to give us, if we integrate, now when you are integrating with respect to x, y is a constant. So this is going to be y is a constant, 6 is a constant, integral of x is x square by 2. Integral of 2y square will be 2y square times x. Integral of 5 is minus 5x plus psi y. So now you find psi. Now we determine psi by using, so we have two things which are given to us. We have used only one of them, so we use the other one to find psi. So now determine psi by using d phi dy is n. So I take d phi dy, if I differentiate this with respect to y, what do we get? I get 6x square by 2 plus 4xy, 4yx, 5x will go away, plus psi prime y, and that is equal to n, and n was 3x square plus 4xy minus 6. So this is same as that, this is same as that, so that gives you psi prime y equal to minus 6. So d psi dy equal to minus 6. So psi y is going to be the integral of minus 6 with respect to y, which is minus 6y. So therefore we got our phi. So this is how you find the potential of a conservative vector field. So phi of xy is therefore equal to, we have this formula, isn't it? So it's going to be 3x square y plus 2xy square minus 5x minus 6y. You can check that this function has the property that its gradient is f. So note that gradient of phi is f bar. Now just to stress this last point, that when you have a conservative vector field and you are finding the integral along any curve, say let's take a curve, well anyway what curve it is, it doesn't matter. If you take 2 points, so let's take in the plane, one point is 1, 1, other point is 4, 4. So what will be, so let's compute the line integral of this function over any curve C, where C is any curve joining 1, 1, 2, 4, 4. So then what will be the answer? So we have seen already as a corollary that line integral of a conservative vector field, if the potential is phi, then this is phi at 4, 4 minus phi at 1, 1. So we don't have to actually parameterize the curve and compute the integral. Once you know the potential, this is easy to compute. So it is 3 times 4 square times 4 plus 2 times 4 times 4 square minus 20 minus 24. That's the value at 4, 4. Minus the value at 1, 1 will be 3 plus 2 minus 5 minus 6. Whatever that may be. That's 64. 64 multiplied by 5, which is 320. Minus 20 is 300, and minus 24 will be 276. Minus 6 cancels 6 minus 5, so it's 271. Good. So now we could find phi by, we could have found phi by integrating n with respect to y also, rather than using integral of m with respect to x. So that depends on the problem. In some problems, one of the integrals can be more difficult. Let's see one more problem. So problem number, I think it is number 2 of the problems on conservative vector fields. So show that the following vector field f bar is conservative, and find its potential. So your f bar of xy is given by y e to the x cos 2x minus 2 e to the xy sine 2x plus 2x I bar. This is a long vector field. X e to the xy cos 2x minus 3 z bar. So here m is y e to the x cos 2x minus 2 e to the xy sine 2x plus 2x. N is x e to the xy cos 2x minus 3. So again, both functions are of class C1 because polynomials and trigonometric functions and exponential functions are of class C1. Their domain is all of R2. So note that we should mention this. Domain of f bar is R2, and it is of class C infinity actually, but all I need is C1. So now consider dm dy. So if you differentiate with respect to y, you get e to the x cos 2x. Then derivative with respect to y of the second term is going to be 2 sine 2x, I write outside. E to the xy derivative is e to the xy, derivative of xy with respect to y is x, and derivative of 2x is gone. dn dx, here we have a product of 3 functions which depend on x, isn't it? Let me just check whether my problem is right. Well, anyway, let's calculate what n is. So n is going to be dn dx is, so it's e to the xy cos 2x because when I differentiate with respect to x, that's what I get. Then when I differentiate the middle term, I get minus plus x and cos 2x stay outside, e to the xy times y, and then I differentiate the last term, which is going to give me plus x e to the xy sine 2x times 2 with a minus sign because derivative of cos is minus, so this is going to be minus. I think I have made one mistake in copying this problem, so let me check one more time because this is supposed to be exact and I don't have exact. Not exact, I mean conservative. I keep on using the terminology of differential equations. So let's see the problem. Problem is 6xy. Let me see where the function is. Yeah, it's y e to the x. It's y e to the xy cos 2x minus 2 e to the xy sine 2x plus 2x plus x e to the xy cos 2x minus 3. Yes, so I missed one x which caused this problem. So there is a x here. So when you write this, there is a, so the m will be xy. So let me correct this. So when you take the partial with respect to y, you get e to the, so let me clear up the partial with respect to y of dm dx, dy. So now when you differentiate this with respect to y, you get cos 2x outside. That has nothing to do with y. Multiplied by 1 times e to the xy plus y times e to the xy times x. And then you will get minus 2 sine 2x e to the xy times x. So now let's check whether these two things are equal. So you have this term right here. This product is exactly this product, and this term is exactly this term. So therefore dm dy equals dn dx, and therefore f bar is conservative. So now we'll try to find the potential. So therefore there is a phi from R2 to R such that f bar is the gradient of phi. So let's see what that says. So that means d phi dx is equal to m, which is, and now I have to copy my m carefully. It is e to the xy cos 2x, y times e to the xy cos 2x minus 2 e to the xy sine 2x plus 2x, and d phi dy is n, which is x e to the xy cos 2x minus 3. So therefore I can write phi either as integral m dx plus some function of y, or I can write phi as integral n dy plus some function eta of x. Now you see that in this particular problem, if you have to integrate the first term with respect to y, with respect to x, you will have integral of e to the xy times cos 2x. It's the integration of exponential and trigonometric. That has to be done by parts, and it is complicated. And then again you will end up having another integration by parts here. So integral of m dx will take long time. You need to use integration by parts twice, and that too the long integration by parts, where each one will need two integration by parts. You remember, if you remember how to integrate exponential times trig functions. So I should add a word very, so it will take very long time. On the other hand, if you integrate n with respect to y, y is only involved in this term, so this is much easier. So in a given problem, you choose which route you want to take, whether you integrate m with respect to x or n with respect to y. So we'll start phi of xy by integrating n with respect to y plus some function of eta of x. And what does that say? This is going to be your x cos 2x are constants because they have x in it. So it will be just integral of e to the xy dy plus eta x. And this integral is, sorry, so let me write this as x cos 2x. The integral of e to the x is e to the x by a. So this is a is your x because that's a constant, plus psi x and x cancel. So this is going to be cos 2x e to the xy plus eta x. And now we find eta by using the fact that d phi dx is m. So d phi dx, you differentiate this function with respect to x, right? And let's see, d phi dx is going to be, so it's going to be minus 2 sine 2x e to the xy plus, when you differentiate e to the xy, you are going to get cos 2x e to the xy times y. And where is my m? Yeah, so let's look at m. So this is equal to m, which is, m was y e to the xy cos 2x minus 2 e to the xy sine 2x plus 2x. So these two terms are the same, and I forgot to add eta prime x. So that tells you that eta prime x is 2x. So eta prime x here stands for derivative with respect to x, so that's 2x. So eta x is the integral of 2x dx, which is x squared by 2, and 2 cancel, so eta x is x squared. So that gives you your phi of xy as x squared plus cos 2x e to the xy. So you can check that the partials, the gradient of phi, you can check that gradient of phi is f bar. So you need to do these problems, and these are, I think I have asked you on homework set 7. So let me summarize. So when a vector field is conservative, when do you say that it is conservative? If it is a gradient of a scalar field. This is equivalent to saying that the line integral is independent of the curve joining 2 points. The line integral only depends on the endpoints. This is equivalent to saying that the integral on any closed curve is 0. So for example, if you are given this complicated vector field, you can find the integral on any closed curve and it will be 0. So you don't have to do any integration. So this is a very important theorem of mathematics. Now you might say, is there an analog of this criterion we saw for checking conservativeness of a vector field in 3D? So this question we will address. Let me take a look at the time. Yeah, I think we can go ahead with this. So question, is there any analog of theorem 2 which I wrote above in R3? And the answer is yes. And for that I will introduce you to a very important concept, and that is the concept of curl of a vector field. So the idea is the following. You will understand this much better at a later stage, but at the moment I can give you the definition. So Let's take a vector field f bar from D, which is a subset of R3 to R3, be a C1 vector field. Then curl of f bar, also denoted by you write this sign cross f bar. This is a vector field. Curl of a vector field is again a vector field. Is a vector field given by the rule, and so I will tell you how to find curl of a vector field. And why is it called curl? This I will explain. So let's call f bar to be MNP. Then this is going to be written as IJK. This is a convenient notation. I'll say what I mean by this. dx dy dz and then MNP. So what this means is you go like what you find the determinant. So you will get this product. So in other words, let me write it like this. d dy d dz np I bar d dx d dz mp z bar, and second term will be negative, right? d dx, what do I mean by this will be clear when I write the last line. So this means it's a vector field which is obtained by a very complicated process, and this process captures something in physics. This is going to be most interesting. This captures this so-called whirlpool motion in a turbulent fluid. How do you like that? But that explanation I give you much later when we will study Green's theorem. But at the moment we will just learn how this is computed. So this is NP. So this is dp dy minus dn dx. Sorry, this is z, isn't it? I bar plus or minus dp dx minus d z dm dz z bar plus dn dx minus dm dy. This is your familiar guy here. In 2D you will see that this is what curl turned out to be. The other two components will be 0 for a two-dimensional vector field. We'll come to that in a minute. But this is the definition of a curl of a vector field. So curl of a vector field, as I mentioned, has something to do with rotational motion. If you think of D as a kind of a set on which there is fluid, and the vector field f bar acts on the fluid particle at xyz, and so it's a turbulent fluid, then the curl of f bar sort of measures the rotational motion that is there in this fluid, which causes vortices. As you see in water rushing into a gutter in during the rainstorm, there are these little whirlpools. That is captured by this curl of f. See how Mother Nature talks in the language of mathematics. So this is not at all an obvious thing, which humans invented these things, and this is the connection between the so-called circular motion within a turbulent fluid. This is going to be captured by curl of f bar when f bar represents the force acting on a fluid particle. That's the physics interpretation. But for us, let's just calculate some, just to get familiarity with this, we'll calculate curl of something. So let's take vector field f bar of xyz to be, let's say, xy I bar plus yz j bar plus x square k bar. Let's find curl of f bar. Okay, so what do? So you write curl of f bar is equal to ijk. This is just a notational convenience so that you remember the formula. Otherwise, who wants to remember it in this form? You just write it as in terms of the determinants. So the first component is yz, second is xy, and then yz, and then x square. So this is going to be partial of x square with respect to y minus partial of yz with respect to z I bar minus partial of x square with respect to x minus partial of xy with respect to z bar plus partial of yz with respect to x minus partial of xy with respect to y k bar. So this curl will be dx square dy is 0 because x and y are completely independent. So this is 0 minus derivative of y with respect to yz with respect to z. Y is a constant, so it's just y. Here you get minus 2x minus partial of xy with respect to z is 0. And here partial of yz with respect to x is 0 and partial of xy with respect to y is x. So the answer will be minus yi bar minus 2xz bar minus xk bar. So that's the curl of the original vector field. Good. Let's do one more. So this is our example 1. So you will see that what happens in the case of two-dimensional vector field. So example 2. Let's take f bar to be mi bar plus nz bar plus 0k bar. Then your curl of f bar will be izk ddx ddy ddz mn0. So what will this be? This is d0 dy minus dn dx dz I bar minus d0 dx minus dm dz z plus dn dx minus dm dy k. And now you see that your m and n depend only on x and y. M is m of xy, there is no z here. N is n of xy. So this will be, so dn dz will be 0 minus dm dz will be 0 plus dn dx minus dm dy k bar. And so this is just dn dx minus dm dy k bar. So in 2 dimensions, you see we found that the vector field is conservative if its curl is 0 vector field. And this is the way the theorem is going to be generalized. So the theorem that we have is that a vector field is conservative in 3 dimensions. The analog of theorem 2 is exactly when its curl is 0. But before we go there, we will observe one more thing and then I will write that theorem. So note that curl of gradient of a vector field is always 0. So lemma. That means if a vector field comes as a gradient of a scalar field, its curl is always 0. So if you are interested in finding the conservative vector fields, it follows that if a vector field is conservative, its curl is 0. And the converse is also true. This is the generalization of the previous theorem, provided of course the domain is simply connected. So lemma curl of grad phi is always a 0 vector field. Let's prove this. So what is grad phi? This is your d phi dx, d phi dy, d phi dz. So what is curl of gradient of phi? This is going to be izk I bar, Z bar, K bar, I should write d dx, d dy, d dz. And then you have d phi dx, d phi dy, d phi dz. So this will be, if I go that way, you will get phi yz, because you are differentiating d phi dz with respect to y. So y, z first, then y. So I should write it the other way around, isn't it? Phi zy minus partial with respect to y and then with respect to z. So phi yz I bar minus phi with respect to z and then with respect to x minus phi with respect to x then with respect to z bar plus phi with respect to y and then with respect to x minus phi with respect to x first and then with respect to y k bar. And this will be 0 bar provided you can interchange the order of differentiation. And so we will need in this lemma phi, let phi be of class C2. C2. So if phi is of class C2, then it follows that gradient of phi is has curl 0. So in particular, this says, therefore, as a corollary, if f bar is a C1 vector field, then f bar is conservative. That means f bar is gradient of phi, implies that curl f bar is 0. We saw this in 2 dimension before. This is the criterion that you get dm dy equal to dn dx. Converse is also true. This is the higher dimensional analog. Is true provided D is simply connected. So this is the theorem. F be a function from D, which is a subset of R3 to R3, be of class C1, D be simply connected, meaning domain without holes, then f bar is conservative if and only if curl of f bar is 0. So in 3D, if you have a function, if you have a vector field in R3 and you want to know whether it is conservative, the necessary condition is you want to check that the curl of f bar is 0, and then you can express it as a gradient of phi. And how do you find this phi? The procedure is going to be exactly as before. So maybe, I don't know whether I should do this now or should I wait for this? Maybe I'll wait for this. So how to find? So for f bar from R3 to R3, or D in R3 to R3 of class C1, we can check whether it is conservative by checking whether curl of f bar is 0, and if it is so, finding phi will be exactly as before. Finding the potential phi, this I will do next time. I will work out one example. Potential phi is exactly as before. exactly as before, meaning that is as in the case of 2D. I think this is a long lecture already, and I think I will stop at this point, and so we will work out an example, and then I will tell you how this concept of curl measures the so-called rotation or the vortex motion in a turbulent fluid. Now time to quit, so let me stop this, and so I'll see you